is talk about the number system and rational and irrational numbers. So you have actually been working with this semester rational and irrational numbers, but we just haven't been calling them those. So we're going to kind of first just go through the definitions of what these different numbers look like and then work on identifying. So natural numbers, these are considered the counting numbers in the natural world. So some examples, 1, 2, 3, 4, 5, and so on. So we call these the counting numbers. Or naturally occurring numbers. So that is always starting at 1. So the way you can think about it, if you were to count how many people were in a room, you would start off with the number 1. So 1 is the very first counting number or natural number in existence, and then 2, 3, 4, 5. Whole numbers is just a step up in complexity. So whole numbers just include the number 0 in addition to all of the natural numbers. So 0 was introduced way later in the world than natural numbers when we talk about the progression of mathematics. So when 0 was added, that created its new set of numbers. So all natural numbers plus 0, or representation of nothing. Next, we have integers. So integers are numbers that are a little bit more complex, but still in this concept of counting numbers. So we have 0, 1, 2, 3, and so on. Integers just now create the inverse or the negative version of that. So as math progressed, we started realizing, okay, you could owe people things. You could have the absence of something, which would be 0, but then you could also have the owing of something, which is where negative numbers came from. So all counting numbers and their negative versions. All right, so we're just progressing down basically into complexer numbers. So we have all of our counting numbers. We threw in the number 0. Now we threw in negatives. So the next thing that we would see is rational numbers, and this is going to include all of your decimals and fractions. Now we have to be very careful here for rational numbers. It would include all fractions and decimals, but a very specific type of decimals. All decimals that terminate or repeat. So we have all of these naturally occurring numbers. So yes, 5 is technically a rational number, but so is the number 5.25 because it's a decimal that terminates. So terminating means you don't have a dot, 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 and you don't have a bar above it. Now, when it comes to repeating decimals, we could see something like this, maybe 3.1212, where it's showing us the pattern of 1, 2 established. And so that dot, dot, dot just means that is going to keep reoccurring 1, 2, 1, 2, 1, 2, which is repeating. Another way this could be written is 0.12 with a line above it. That is also another way of writing repeating numbers. You could also have fractions, so something like 2/3. That would be any fraction is a rational number because all fractions can be written as these types of decimals, so all fractions. And then obviously you could have their negative version, so like a negative 2/3 and negative 5.25. The negatives are still also an option. Now, what we're going to see from rational to irrational is a transition into the numbers we've been working with, which are radicals. So one of the first types of radicals that you're introduced to is something like this, the square root of 25, which is technically a whole number. Actually, it's considered a natural number in its basic form. So some radicals are actually rational numbers because they simplify to whole numbers. But what we have started working with is radicals that don't turn into a perfect square. They can simplify, right? We could simplify this to 3√3, but it still has a radical. And if it still has a radical, that means it is a number that is non-terminating and it has to be the word and included, and non-repeating. So it has to meet both conditions. So what we'll see, or repeating here. Sometimes we'll see this in our calculator. If you were to actually square root the number 27, so I could do square root 27, it gives me this decimal, and obviously the calculator doesn't have the capacity to keep going forever. It's not going to give you a dot, 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 but if we see all of these here, this is showing us non-repetition, and it's also non-repeating and non-terminating. So with that, another type of number we could see is something like this. And this is one that really will confuse some people sometimes. So let's say we have 3.12, 112, 1112, dot, dot, dot. This is where people tend to get messed up. This is a non-repeating number, but you see a pattern. And what you have to remember is patterns are not repetition. Could you predict what comes next? Yeah, probably it'd be a 1, 1, 1, 1, 2 that comes next, but it is not repeating the same exact thing over and over again, so this is technically irrational. Now, we have seen a couple other irrational numbers. We could see something like 4.68312, dot, dot, dot. That has no pattern established. The dot, dot, dot means it doesn't stop, so it meets our conditions. But we also have one more number that you guys have been working with since elementary school, which is pi. Pi is irrational. It's just such a commonly used irrational number that we have a symbol for it, but pi is technically irrational. So looking at this grand scheme of things, when we're talking about the number system, we have rational numbers and irrational numbers. And irrational numbers are its own small little category. So one thing we want to make sure we understand is that all rational numbers have everything included under it. So we start off with natural numbers. Then we learn about whole numbers. Integers come next. And then we have rational. And all of these build on each other. So all rational numbers have these subcategories included. So a natural number is technically a whole number, an integer, and a rational number, right? Because 3 could be written in all of these, right? Now, a whole number, some whole numbers are not natural numbers, but all whole numbers are integers and rational. Moving into integers, integers include negatives. So not all integers could be whole or natural, but all integers, they are part of the rational number system. And then the last concept, right, if we have 4.25, this cannot be an integer, it can't be whole or natural, but it is still part of the rational system. And then irrational is so different. It's such a different concept that we have its own little category over here. It has nothing to do with this rational number. So it's important we visualize the difference between these two. Now, we're going to look at just identification, and I'm going to take you through about half of these and work on identifying whether these are rational or irrational. Which system does it belong to? So this first one, 0.36, this is going to be considered rational because it is a terminating decimal, right? It stops. Next, we have 36, 36, 36, 36, 36, dot, dot, dot. This is also going to be considered rational because it is a number that is showing repetition that is continuing forever, so the pattern is established. Next, this is going to be considered rational as well because we have that bar above it, which means repeating. And then this one, we have a pattern established, 36, 336, 3336, dot, dot, dot. Now, technically, I know what could come next, 3336, but this is considered irrational because it's a pattern, not repetition. We would have to see 3636 over and over again. 5, now remember, we have to check this one out. This is the root of 8. This does simplify. We learned about simplifying, but even when we simplify, we still have the radical. The only time a rational number could be a radical is if it simplifies as a perfect square. This is not the case, and so it is irrational. Next, we have 10 times pi. So if you don't remember, pi is technically the number 3.14159 ... So if you were to just multiply it by 10, that would just move it 2 places. So it would be 314.159 ... So we still have a decimal that continues for forever. So this is also irrational. Next, we have this 1, 2, 1, 3, 1, 4, 1, 5. So we see it's not repeating, okay? But what is it missing here? A ... which means this actually stops, right? This is a stopping decimal, which means it is in fact rational. Square root of 16. Let's check to see if it is a perfect square. Because we have all pairs that come out and no singles, it is in fact a perfect square, which makes it rational. So what I want you guys to do is pause the video and try 9, 10, 11, 12 on your own. And then we'll check those after you do it. So go ahead and pause the video and check. All right, so 8, 9, or 9, 8, 9, 9, 8, 9, 9, 9, 8. It is a pattern, but it is not repeating, so it is irrational. Number 10, it is terminating, so it is rational. 121 is a perfect square, so it is rational. And then here, remember the idea is 3 plus 3.14159. So this just becomes 33.14159 ... right? It continues for forever. It has no pattern or repetition, so it is irrational. And that is it. So we will pick up with identifying rational and irrational the next day. So that is it for your video notes.